If you've ever used a chatbot to help you out with a tricky problem, maybe you were trying to debug some messy code or figure out a really complicated travel itinerary, you have probably stumbled onto one of the most famous cheat codes in all of generative AI. You just type the words, think step by step.
Yeah, it is. It's basically the closest thing we have to a magic spell in prompt engineering. You just append those four words to the end of a prompt, and suddenly the model goes from giving you this, hallucinated, chaotic mess to a beautifully structured, logically sound answer.
Right, it's wild. But here's the thing we were exploring today, like, why does that actually work? So welcome to this deep dive, where our mission is to unpack a foundational, state-of-the-art paper from AI researchers Wenlong Wang and Fergal Reed. The paper is titled, Does Verbose Chain of Thought Really Help? In distribution evidence that content, not length, matters.
And we are going to look way past the industry hype today. What we have here is a piece of highly controlled experimental research that looks at the very mechanics of artificial intelligence. It gets right to the core of how these models actually process information behind the scenes.
Exactly. And whether you are a developer building massive Gen AI applications or, you are just someone trying to get a better answer out of ChatGPT for your daily tasks, understanding how these models actually think is going to completely change how you approach them.
It really will.
So let's just unpack the core mystery right off the bat. When we tell an AI to think step by step, it generates a long chain of thought, right? It spits out way more words before giving us the final answer.
Yeah.
The big question this paper asks is the AI getting smarter because of the actual semantic facts inside those extra words? Or, does forcing it to spit out more words simply give its neural network more computational time to process the math in the background?
Right. And this is like the great debate in AI research right now. To really grasp the stakes of this, we need to look at the two competing theories the researchers are testing. So the first theory is the semantic trace hypothesis.
Semantic trace, meaning the actual literal meaning of the words being generated.
Exactly, yeah. This hypothesis argues that chain of thought works because the AI is explicitly writing down useful facts, mathematical operations, and intermediate values. It is essentially creating a human-readable scratchpad for itself.
Oh, I see.
Yeah, so when it needs to calculate step 4, it can simply look back at the text it generated in step 2. It relies entirely on the semantic content of the language it just produced.
Okay, so then the alternative to that would be the forward pass computation hypothesis, right?
Yes, exactly. So this theory suggests that chain of thought works primarily because generating more tokens, which are just the chunks of words or characters the AI produces, forces the model to perform more sequential computations.
Right.
Because in the architecture of large language models, every single token generated requires a full forward pass through the neural network.
Okay, but let's unpack this with an analogy. So it's like asking if a student does better on a complex math test because they're explicitly writing down all their formulas and carrying the ones, which would be the semantic theory, right?
Yes.
Or simply because forcing them to sit in the exam room for an extra hour gives their brain more time to subconsciously churn on the problem in the background, which is the compute theory.
I love that analogy. It's spot on. The question is whether they are using the paper as a genuine tool to store information, or if we are just, trapping them in the room to buy their brain more processing time.
Right, right.
And answering this question is incredibly urgent. The architecture of AI is evolving so rapidly right now. We are seeing the rise of newer models like loop transformers and models that use what is called latent space reasoning.
Oh, latent space reasoning.
Yeah, these newer models are deliberately designed to trade away human-readable steps in favor of raw, hidden computation.
So they basically do the thinking in a black box, so we don't actually see the steps at all.
Exactly. We only see the final answer. And if we do not fundamentally understand why chain of thought works right now, whether it is the readable words or the hidden compute time, we are not going to understand how these future, more opaque models operate.
We have to understand the present to predict the future.
Yeah.
But the challenge is, you can't exactly interview a neural network and ask it how it feels about its processing time.
Yeah.
You just have to observe it.
Right. You can't just ask it. So the researchers set up an incredibly rigorous experimental observation. First, they wanted to see how AI models behave naturally without any forced human intervention or rewriting of their prompts.
Just letting them do their thing.
Exactly. They observed 25 different models. This included major open-weight players like Qwen3, Mistral, and DeepSeek R1 Distill.
Wow. Okay, so a very broad sample size of the current state of the art.
Very broad, yeah. They took these models and asked them the exact same math questions repeatedly using a technique called temperature sampling. This basically allows the AI to generate a variety of natural responses.
Oh, right. So it's not the same exact answer every time.
Exactly. Sometimes the AI will be brief, and sometimes it will naturally be very verbose and wordy.
But wait, hold on. If you are just letting the AI ramble naturally, you run into a massive variable control problem. Like, couldn't the longer, wordy version just be a totally different, messier train of thought that happens to arrive at the same destination as the short version? You wouldn't be comparing apples to apples.
That is a great catch, and the researchers knew that, so to solve that, they used a value-agnostic structural prefilter.
Okay, let's translate value-agnostic structural prefilter for anyone who doesn't spend their weekends reading AI white papers. Basically, they used an algorithm to strip away the actual numbers and just look at the skeleton of the math steps, right?
Yeah.
Like mathematically hashing the logic to prove the dependency structure of the arithmetic operations was identical.
You nailed it. They mathematically proved the steps were structurally identical. And then to add another layer of verification, they used independent, highly advanced LLM judges to blindly read the paired answers.
Just to double-check the logic.
Yes, they needed to verify that the two traces were using the exact same logical blueprint. They paired a naturally short, concise generation from a model with a naturally long, verbose generation from that exact same model, ensuring both use the identical reasoning plan.
Okay, so they have ironclad proof that the AI is taking the exact same logical path, just using way more words in one version than the other. So when the AI naturally talks more about the exact same plan, the expectation might be that the extra processing time boosts its score.
You would think so, right? But across almost all of the independently trained reasoning models, the extra length did absolutely nothing to improve accuracy.
Wait, nothing?
The accuracy difference was basically zero. On a major math benchmark, the difference between the verbose and concise accuracy was literally negative 0.005.
Wow, it's just statistical noise. So just forcing a model to blabber on longer about the same exact math problem doesn't magically make the math better. The forward pass compute theory, just buying it time, completely falls apart in a natural setting.
It completely falls apart. The blind analysis showed that pure verbosity, just elaborating or restating things, never discriminated a winning answer from a losing one. The only time extra tokens actually helped improve the final answer was if those specific tokens contained actual validation or checking steps.
Oh, like checking its work.
Exactly. For example, if the AI explicitly wrote, "Let me plug this back into the equation to test it," that specific semantic work mattered.
Right, so it's not the sheer volume of the words, it's the specific job those words are doing. But, watching them in the wild can only prove so much. I feel like to definitively prove this to a skeptic, you'd have to strip away that natural behavior entirely. You have to force the AI into a controlled lab environment where you dictate exactly how wordy it's allowed to be.
And that leads us to leg 2 of the experiment. The researchers needed to forcibly rewrite the AI's thoughts.
Right.
To do this without breaking the model's logic, they used a concept called directed acyclic graphs, or DAGs. Think of a DAG as a flowchart that only moves forward. It is the raw, underlying computational blueprint of a math problem.
Okay, so no going backwards.
Right. It strips away all the language and just looks at the nodes of computation and how they explicitly connect to each other.
So if the problem is John has 6 apples and buys 8 more, the underlying structure, the DAG, is just node 1 is 6, node 2 is 8, operation is add, result is 14. It's the absolute raw skeleton of the logic.
Exactly. The researchers extracted these raw DAGsy skeletons. Then they forced the target AI models to read a rewrite of that exact same DAG. They created a concise rewrite, which they called L1, and a highly verbose rewrite, which they called L4.
The L1 trace would just be the bare minimum, right? Something like 6 plus 8 equals 14. Done.
Yes. While the verbose L4 trace, expressing that exact same DAG flowchart, would be expanded into this big narrative, the text would actually say something like, starting from the initial count, we have 6 toys. He then acquires 8 more, which by simple addition gives him a total of 6 plus 8 equals 14 toys.
So it's the exact same map, but the L4 version sounds like a Victorian novelist trying to hit a word count.
Exactly.
But wait. If you feed an AI a verbose version that sounds like a Victorian novel, how do you even grade that fairly? Because a strict, automated math grader would probably reject it just for having too many words, even if the final math is correct. They would just get lost in the prose.
And that is exactly why the researchers introduced a dual validator design. They used 2 different judges to evaluate the AI's performance. The first judge, E2, is a strict algorithmic validator.
Okay.
It looks at the parsed structure of the math, searching for really rigid patterns. And under E2, they saw a pretty big accuracy jump, about 5 to 10% higher accuracy when the AI was fed the verbose L4 prompts.
Wow, a 5 to 10% jump is massive in this context. But based on how rigid automated graders are, I mean, there has to be a catch.
There is a massive catch. It turned out that E2, that algorithmic judge, was heavily biased against verbose text in general. It was systematically rejecting perfectly good, accurate, long answers from the baseline models just because they had too many words that didn't perfectly align with its rigid regex formulas.
Oh, I see. So E2 is like the incredibly strict math teacher who docks points if your explanation is too wordy, even if the math is completely flawless. So it was artificially inflating the success of the L4 prompt by unfairly punishing the natural verbose answers.
Precisely. That required them to look at the second judge, E3. E3 is a broader LLM judge, a local evaluator calibrated against advanced models like Claude Sonnet.
Okay, so a smarter judge.
Much smarter. E3 is much better at understanding the actual narrative context of the math rather than just hunting for rooted syntax. And when E3 evaluated the results, that massive 10% gain just vanished.
But it didn't drop to zero, right?
No, it didn't. It settled at a much more modest 1 to 4% boost in accuracy for the verbose L4 prompts over the concise ones.
So E3 is basically the English teacher who appreciates the narrative context and doesn't unnecessarily penalize the word count. But still, even at a 1 to 4% gain, it is deeply counterintuitive that just adding narrative fluff to the exact same math problem gives the AI a measurable boost in getting the final answer right. Like, why would the AI care about the phrase starting from the initial count?
Right, and that was the big mystery. The researchers needed to know if the AI was just succeeding because the long, verbose text happened to repeat the numbers 6, 8, and 14 more often.
Oh, right.
Essentially making them easier to copy and paste into the final answer.
Because if you hide the answer in a giant block of text, maybe the AI is just really good at playing a game of Where's Waldo with the digits. It sees the number 8 3 times, so it assumes 8 is important.
Exactly. So to isolate that variable, they ran the maximum numerical redaction experiment. And this is brilliant. They took the verbose math prompts and they scrubbed out every single number. They replaced every digit with a placeholder tag that just said redacted.
Here's where it gets really interesting. So instead of 6 plus 8 equals 14 toys, the AI is literally reading redacted plus redacted equals redacted toys.
Yes. Every single number is gone. Now, the natural assumption is that the AI would completely fail. How can a system process a mathematical reasoning task without the actual numbers?
It sounds like an impossible Mad Libs game.
Yeah.
Blank minus blank equals blank. If there are no numbers to do math with, the extra text shouldn't be doing anything for the AI.
Yet, not only did the AI not fail, the verbose helps effect was actually amplified.
Wait, amplified?
Yes. What's fascinating here is that the median amplification across 4 different arithmetic benchmarks was 3.24 times. The benefit of the verbose text skyrocketed when the numbers were taken away.
That is wild. When you take the numbers away, the long, wordy story helps the AI more than it did when the numbers were actually there.
Think about what happens to the concise prompt when you redact it. The L1 prompt was simply 6 plus 8 equals 14. If you redact that, it becomes redacted, redacted, redacted. It is a completely useless, meaningless string of placeholder symbols. There is nothing for the model to latch onto.
Oh, I see it now.
But the verbose L4 prompt, even with the numbers gone, retains its prose-level reasoning structure.
It retains the entity relationships, the actual action structure of the problem.
Exactly. The narrative of the logic is entirely intact.
Yeah.
Starting from the initial count, he then acquires more. Subsequently, toys are given away.
Right. It's giving the AI the scaffolding of the logic. It's explicitly telling the AI how to think about the relationship between all the missing variables, rather than just handing it raw data and hoping it figures out the relationship on its own.
Yes, it proves definitively that the AI is leaning heavily on the linguistic structure to guide its logic. It is not just extracting raw numerical data. And to put a final lock on this, they ran one more test.
What was the last test?
They took the short L1 prompt and they padded it with non-reasoning filler words until it was the exact same length, the exact same token count, as the verbose L4 prompt.
Oh, so just absolute fluff. No logic, no entity relationships, just pure word count to test the compute theory.
Exactly. And the filler did absolutely nothing to improve accuracy. The accuracy stayed clustered right at the bottom, exactly matching the performance of the short prompt.
So that is the definitive end for the pure forward pass compute theory. Adding meaningless filler gives the AI the exact same amount of extra computational time. It forces the neural network to do the exact same number of forward passes. But it doesn't help at all.
Not even a little bit.
So it is the quality of the prose, the actual logical narrative, not just the token count.
It is what the tokens do, not how many there are. The researchers concluded that chain of thought helps primarily through semantic content, but competent verbose elaboration adds a further prose level affordance that the model can actually condition on. The language itself maps the path to the answer.
This completely reframes how we should think about prompting. But, before we declare victory for verbose narratives across the board, we really need to acknowledge the limitations here. Up until now, everything we've talked about is based on mathematical and symbolic reasoning benchmarks with names like GSM-8K and Math 500. But if you are using an AI in your daily life, you aren't always asking it to do math.
Right. And the researchers recognized this limitation and tested non-arithmetic benchmarks, too. These are tests that measure common sense reasoning, like strategy QA.
Okay.
These are questions that require logic, but not necessarily strict mathematical formulas or procedural flowcharts.
And on those common sense tasks, the whole Victorian novelist approach totally backfires.
The narrative flips entirely. For 2 out of the 4 model families, they tested on common sense tasks. Specifically, Microsoft's Phi 3 Mini and 0.1 AI's Y1.59B verbose chain of thought actually hurt their accuracy. It degraded their performance significantly.
Wow. Okay, so this domain dependence is a vital takeaway. It shows that while narrative structure heavily scaffolds mathematical operations, overloading an AI with verbose steps for a simple common sense question actually confuses it.
It does.
It's like if I asked you if it's raining outside, and you started giving me a 5-minute monologue about the barometric pressure, the history of meteorology, and the dew point. By the end of it, you might get so tangled in your own words that you forget if you actually looked out the window.
That's exactly it.
Yeah.
You derail your own logic with unnecessary exposition. It is a profound realization about how fragile and context-dependent these models can be. They are not, uniformly intelligent in the way a human is. Their reasoning is deeply tied to the structure of the language we force them to generate.
This is a huge, actionable pro tip for you listening right now. If you're using AI for data analysis, complex coding, or multi-step math, tell it to explain its work. Give it the space to build that narrative scaffolding.
Absolutely.
Prompt it to provide high-quality, structured validation steps.
Yeah.
Ask it to explicitly explain the relationship between its variables. But if you're just asking it a basic logic or trivia question, forcing it into a long-winded chain of thought might actually make it hallucinate or trip over its own words. Keep it concise for common sense.
That is the perfect summary. The ultimate conclusion from Wang and Reed's paper is really clear. The theory that we can just force an AI to churn longer in the background to get smarter is dead in the water. It is the structure of the thought, not the duration of the thought.
So what does this all mean for you? Well, pure length is not enough. Adding meaningless filler doesn't make an AI smarter. What actually boosts performance is the semantic content and the prose quality of the reasoning structure. It's the verification steps and the clear entity relationships. But, this paper leaves us with a rather haunting implication for the future of AI.
We touched on this earlier regarding the growing trend in the industry toward latent space reasoning. Future AI models are currently being trained to do all of this complex computation entirely in their hidden layers. They are being designed to stop generating human-readable English steps.
So they won't output the think step-by-step text at all. We won't see the L1 or the L4 trace.
No, we will only see the final answer. But this paper just proved, with the maximum numerical redaction experiment, that current AI relies heavily on the prose structure of English words to help keep its logic on track. It needs the linguistic narrative of human language to do complex math effectively.
So if they strip the English out and they stop relying on verbs and nouns to build their flowcharts, what happens to the logic?
That is the million-dollar question. When AI completely abandons human language to do its thinking in the latent space, will its reasoning become completely alien to us? Or will the neural networks discover some pure mathematical language of thought that is infinitely more efficient, but that human beings cannot even begin to comprehend?
It's wild to think about. We started by talking about looking at an X-ray to see a broken bone, something clean, visible, and easy to diagnose. But if AI stops using our language to think, that X-ray machine doesn't just get murky. The screen goes completely black. We won't just be wondering why the AI got the answer. We might not even be capable of understanding its thoughts if it tried to show us. Definitely something to mull over the next time you tell your chatbot to think step by step.